How many different ellipses do you see here? Well, there are three, of course, but if you look at these two, they look pretty much the same. It's just that the one on bottom is smaller. It seems like if you zoomed in on the ellipse on the bottom here, it would look very much like the ellipse in the upper right. The ellipse on the right here, though, is very different. It doesn't matter how much you zoom in or out, it looks very different than the other two. So what we're seeing here is that what matters, what makes an ellipse what it is, isn't just its semi-major axis and semi-minor axis. It's actually some combination that gives the ellipse its overall shape. The traditional way to measure this overall shape of an ellipse actually doesn't involve the semi-minor axis at all. It involves the semi-major axis, which remember we call A, and the focal radius, which remember is the distance from the center to a focus, and we called that C. And so what you do is you take the focal radius, C, and divide it by the semi-major axis. And this gives you a number that is somehow characteristic of the shape of the ellipse. This is called the eccentricity of the ellipse. So ellipses with different eccentricity look genuinely different. Ellipses with the same eccentricity might be larger or smaller, but they look pretty much the same, just like these two ellipses on the left here. So comparing the ellipses on the left to the ellipse on the right, it looks like if you compare the semi-major axis to the focal radius on the left, it looks like maybe the semi-major axis is half again as big as the focal radius. So that means that C over A is going to be about 2/3, I think, for these two. This is an incredibly rough approximation. But for this ellipse on the right, if we sketch the semi-major axis and the focus, it turns out the focus is going to be somewhere way out here because this ellipse is so sort of long and skinny. So A is this top distance and C is this bottom distance. So for this ellipse on the right, it looks like C over A is actually going to be much larger because C is a much larger fraction of A. So maybe this time it's something like 0.9. So eccentricity, a larger eccentricity means sort of a more stretched ellipse, and a smaller eccentricity gives you a more rounded ellipse. Just to see all of this put together, let's look at lots of ellipses all at once. I have a GeoGebra set up so that I can move the vertex of the ellipse and the focus, and it will automatically graph the ellipse that's produced by that vertex and focus. Remember, by changing the vertex, what I'm really changing is the semi-major axis. So if I move the vertex around, the semi-major axis changes. So larger semi-major axis means a larger ellipse. Smaller semi-major axis means a smaller ellipse. And if we move the focus, same kind of thing. So what we can do is highlight the distance from the center to the focus, so that's the focal radius. Right now it's 3.1, and also highlight the semi-major axis. Now remember, the semi-major axis is the distance from the center of the ellipse out to this vertex, but also we've seen the same distance is from the focus up to the top of the ellipse, like this. So right now that's 4.84. And then if we calculate the eccentricity, that's the focal radius over the semi-major axis, we get that right here. So for this particular ellipse, it's about 0.64. As we move the focus closer to the origin, that makes the ellipse rounder, and you can see the eccentricity is getting smaller. When the focus gets all the way to the origin, remember there are actually two foci, so if one of them is on the center of the ellipse, then both of them are, and then the eccentricity is 0. And this is a perfect circle. So a circle is just an ellipse with eccentricity 0. Then if we take that focus and make it, slide it further towards the vertex, then the semi-major axis is staying the same length, but the focal radius is getting larger, and so this ratio is also getting larger. And as it gets very close, you can see two things happen. So one is the ellipse gets very flat, very stretched out, and also the eccentricity gets larger and larger, closer and closer to 1. When the focus gets all the way to the vertex, then the eccentricity is exactly 1, but also the ellipse sort of degenerates into a flat line. So that's probably not really an ellipse. So the general idea here is, for an ellipse, a larger eccentricity means a longer, flatter ellipse, and a smaller eccentricity means a rounder ellipse, and a 0 eccentricity is actually a circle. So let's look at a couple examples. Let's find the eccentricity of this ellipse. Well, to find the eccentricity of an ellipse, the first thing we have to do is figure out A and C. Right? To find the eccentricity, we need A and C, because the eccentricity is just C over A. This equation isn't set up to really show us what A or C is. Actually, we need to rewrite these so that they look like x squared over something plus y squared over something equals 1. And we need to do this in such a way that it's equivalent to this equation up here. So it looks like we should be able to write x squared over 1 over 4 and y squared over 1 over 9. And that works because the reciprocal of 9 is 1 over 1 over 9. Sorry, 9 is 1 over 1 over 9. So these are really the same equation here. And 4 is really 1 over 1 over 4. Okay, and that means this denominator, right, that's since this is the bigger denominator, that must be a squared. And 1 over 9, that's the smaller denominator, that must be b squared. And so a is the square root of 1 over 4, and that's 1/2. And b is the square root of 1 over 9, and that's 1 over 3. But to know the eccentricity, we need to know the focal distance c. But as usual for an ellipse, b squared plus c squared is equal to a squared. So c squared is a squared, which is 1 over 4, minus b squared, which is 1 over 9. And then we need to take a square root. So this isn't going to come out nicely, so I'm just going to punch this all into a calculator. So 1 over 4 minus 1 over 9, and then square root of that, 0.373 approximately. And now finally we know c, so we can calculate the eccentricity. It's 0.373 over a, and a is 1/2. So 2 times 0.373, so times 2. 0.746. Okay, so there's our eccentricity. Let's look at another example. Let's find the equation of this ellipse. So it's an ellipse with a focal radius of 5, eccentricity 1/2, and its major axis is vertical. Okay, so since its major axis is vertical, that means we're going to use the version of the equation of an ellipse where b is under x, like this. So x squared over b squared plus y squared over a squared equals 1. And let's see, we don't know a or b right now. We know the focal radius, so that's c. And we know the eccentricity. And remember, the eccentricity is c over a. So we know c, it's 5. And c over a is the eccentricity, which is 1/2. And then we can solve this for a. So multiply both sides by 2, multiply both sides by a, you get 10 equals a. So the semi-major axis is 10 here. So that fills in one gap in the equation for our ellipse. Now we need to fill in the other gap by finding the semi-minor axis. And so that's b, but as usual, b squared plus c squared is a squared. So b squared plus c is 5, so b squared is 25, equals a is 10, and so a squared is 100. So now we can find b squared. B squared is 75. And if we needed to know b, we could find b as well. This is the square root of 75, which I guess is going to be something like 5 root 3. And then we can fill in the blanks in our equation here. So the equation is x squared over b squared is 75 plus y squared over a squared is 100, equals 1. And so there's the equation of our ellipse.